interesting. So our next speaker is Lorenzo Orecchia, and he's going to tell us about continuous methods.
So I did not pick the title again, so it's rather broad. But this is the first in a series of 4 talks, the second one of which will be right after lunch. And then on Friday, we'll have 2 other talks that will focus more on applications of these continuous methods. And today what I want to focus on is really taking the theme of this program at heart and bridging the continuous and discrete in the design of first-order methods. Okay? And here, really, when I say continuous, I really mean continuous. Not continuous like this. I really mean continuous like this. Okay? So, and part of my rationale for doing this is that a lot of the problems we have in the discrete setting have a specific structure which sometimes is not captured by the kind of standard assumptions people take in this world, in the design of, say, first-order methods for convex optimization. And so if we want to come up with a better way to fit our methods to the specifications and the properties of the discrete world, we need really to go back all the way to the origin, to where these first-order methods come from, which is continuous dynamics. Right, so I also like this continuous point of view on first-order methods a lot, because it allows you to first unify the understanding of lots of different methods, but also really to approach the design of an iterative algorithm in a very principled and almost mechanical way. And that's the main takeaway that I want you to take away from this hour here, is how more than specific technical results, I want you to take away what kind of principle you want to keep in mind when you try to understand or design a first-order method, be it for a discrete problem or a continuous problem. Disclaimer here, I'm going to be morally correct in most of the math, but there are going to be a few things swept under the carpet. Feel free to point them out. But we have a draft of a paper that contains all the proofs, and then we worked thoroughly through all the derivation. And I should just mention that you can find that on the web page of my postdoc, Jelena Diakonikolas.
Later today.
Soon, later today. That's something. We wrote it. Okay. Right. So I should mention also I'm not going to mention lots of references because there's a vast area, but I should mention that recently there have been a number of papers trying to understand first-order methods from this continuous dynamic point of view, and including papers from a number of people here. And the one thing I want to do different today is, rather than focusing, I want to think about these first-order methods as discretization of physical systems. And rather than thinking about my physical system in a Newtonian mechanics point of view, when I think of a particle and I say, oh, there is a gradient, like a force pulling me this way, there is a potential pulling me this way, what's the equilibrium? I'm going to take a more interesting point of view, which is a kind of analytical mechanics point of view, which is that there are some invariants that are preserved in this system, and I want my particle is going to follow the path that preserves a certain invariant. And these invariants are actually very useful because they turn out to be related to the duality gap, to the quality of the solution. So a certain quantity related to the current quality of the solution is preserved throughout all these dynamics. I also like the fact that Lagrange is Italian, which helps. You might think he's French, but he's Italian. Look it up. And I also like that this provides a kind of a connection to lots of areas of physics and dynamical systems that are very interesting. Okay, so let me first talk a bit about the the simplest kind of model, which is the model we'll be working with today, is the kind of convex optimization with a first-order oracle. And it's very simple. You're trying to minimize the convex function. And you have the way this convex function is presented to you is through a black box. So you feed it a point x, and you get back the function value and the gradient. Turns out you don't even need the function value. The gradient is enough. But let's say you also get the function value. And everything is exact. The function is convex. So you have lots of assumptions you can make. And your goal is to ask, in discrete time, your goal is to ask a small number of queries to this black box, and then output some x, which is only epsilon away from the optimum in function value. So in continuous time, things look a bit different. Essentially, you can instantaneously query this box. And at every time t, you get the function value and a gradient. And then you can use these two values from the black box to define a dynamic. So you can write an ODE, an ordinary differential equation that involves these terms, and evolve your system in that way. So the most basic thing you can do is called gradient flow, which is the time derivative of your x equals exactly the gradient. So you move in the direction of the gradient. So I'm going to use this dot notation to mean the time derivative. So this is dx dt. And then the kind of analysis that we'll try to do is to either use a conservation principle or a potential principle, which in this case is called the Lyapunov argument, to get convergence, to get asymptotic convergence of a dynamic. And then we're going to use very simple, like well-understood schemes in the numerical analysis of ODEs to discretize these curves. Because these curves are useless if we cannot discretize them.
So you don't have a scale factor of step size. You just
we're going to build it in. This is for very basic. We're going to build in the step size. And that will be necessary because different methods will need different step sizes. And you can also incorporate adaptive step sizes. So step size is fundamental. And that's when it comes in. Step size comes in discretization. There is no step size in the continuous world. And I should mention, in the continuous world, you can rescale time. There is no issues of convergence. Like if your algorithm, if you write it down in a way that you get convergence in like t squared, you can rescale t squared to be your new t. And you still get, you shouldn't take the ODE behavior is not going to tell you much about the actual convergence. The actual rate of convergence. It tells you about the convergence at infinity. To really understand the convergence, you need to understand the discretization. Okay, so I think when I started to look at this, the first thing I thought about was, gradient flow seems great because it makes you move in a direction that always reduces the function value. So why should there be anything else? Why should we do anything else than gradient flow? Well, the corresponding discrete algorithm is gradient descent. And there are a few arguments why gradient descent and gradient flow do not cut it. The first argument is that some functions are non-smooth. When I say non-smooth, it means that the gradient can change abruptly. So the gradient is not Lipschitz continuous. So in this case, at this point, the gradient all of a sudden jumps up. And that's an issue for the discretization of gradient flow. Because when you're doing gradient flow, if you are here, if you're on this bit of the curve, you really would like to take a long step because you're seeing this very steep slope. But if you take a long step, you're going to overshoot completely. On the other hand, you might be on this side of the curve, and then you should take then you are inclined to take a small step, but really you should take a long step. So you don't have any information about this kind of problem if the gradient can change arbitrarily quickly, and so discretization is a big obstacle for non-smooth functions. And we'll come up with a way to deal with that explicitly. And then there is another issue, which is even more fundamental, is that knowing that the function value decreases is actually very little informative in terms of proving a rate of convergence. Because you need to know compared to what? Compared to where the optimum is. We want to prove something, we want to prove a theoretical bound on convergence. So in a way, not only we need to decrease our function value, but we also need to construct some kind of lower bound to optimum and prove, or at least implicitly prove, that those two converge together. So the real idea is that the real thing we should try to optimize is not really the function value, but is some notion of duality gap. So in the first part of the talk, we really try to focus on what this notion of duality gap is. Okay. Okay, and actually, to give an example of what happens is, here are two dynamics. This is the gradient flow dynamics. It corresponds to gradient descent. And this is something called the accelerated dynamic. And so this one may look like it's longer, and it doesn't have this nice smooth behavior as gradient descent. But this one, the red curve, leads to faster algorithms for two related reasons. One reason is that this red curve is actually trying to optimize the notion of duality gap. And the other reason is that even though this curve is longer, you'll notice that it has longer straight segments. So this curve is actually easier to discretize. This kind of corresponds to what people, in this case, this is actually a smooth, strongly convex function, and this comes actually from a linear system, and this would actually be related to Chebyshev iteration. Okay, so let me start to put down some markers. So the way we want to think of our algorithm is that at every iteration, we have some candidate solution, which I'm going to call x bar. And that x bar is going to define an upper bound to our objective. And at the same time, we want to use the gradient information we are recovering to also define the lower bound. And our goal is to somehow show that those upper bounds and lower bounds are close to each other. And we're actually going to, you can actually explicitly maintain these upper bound and lower bounds. I'm going to call them UT and LT. And notice that UT may be the function value at x bar. It might also be something else. It might be a relaxation of it. So in some sense, what we'll see is that our choice of what we call upper bound and lower bound is going to determine what our algorithm looks like. And eventually, we want to show statements of this kind. The duality gap, which is upper bound minus lower bound, is less than epsilon for some large enough t. Okay, so that's the way we're going to handle. You're going to think about duality gap. And as I said, that the whole, in this way of presenting things, the algorithm is completely determined by your choice of upper bound and lower bound. So you tell me what is your upper bound, what is your lower bound, and there's a box that spits out an algorithm. Okay? Because essentially this upper bound and this lower bound will define this physical invariant I'm talking about. And so this works great for the continuous world, but then you also care about discretizing. So the other thing, what this allows you to do is you're going to pick upper bound and lower bound in a way that guarantees that you can discretize the continuous dynamic that you get. And the main concept in this discretization step is that we are going to care about whether our functions are smooth or not. And we're also going to care about what kind of primitives we have available. Because you'll see that, in general, just having a gradient oracle is not enough to solve these problems. Okay, so let me tell you quickly, more precisely, what I mean by smoothness. So a function, convex function f is smooth on x if it's if the rate at which the derivatives change is just an L. Okay, so here I'm sweeping lots of stuff under the bracket. There is, I'm assuming, I should say in this talk, I'm always assuming that f is differentiable. You can still do convex optimization even if your function is not differentiable. Convex function has something called subgradients. But just think when all of what I say is actually applies to the non-differentiable case. Just imagine that this gradient of f is a choice of subgradient at the point. So let's not worry about subgradients at all. So this condition of smoothness is actually important because it will allow us. It's important for the ODEs we'll write because it will essentially ensure that a solution exists to these ODEs. And it's very important for the discretization because intuitively, if you are if you want to do gradient descent, say, and your function is smooth, so the gradient changes in a controlled way, you can take a step, and as you take your step, in the beginning your step is completely parallel to the gradient field, and as you move, it's going to stay parallel for at least some stretch, and in that stretch you are making progress. Okay, so that's the whole idea of smoothness, is that it allows you to say, I can make a step that is at least a certain length, because within that ball, my gradients look like the original gradient.
What's the star?
The star. Okay, so the norms that I use on this talk are general norms. So this could be the primal norm, and it is the dual norm. So you can think of L2 and L2. You can think of L1 and infinity, and this is general for non-Euclidean norms. And also more complicated norms. So there are many ways. So the way I chose to present this involves giving you some rudiments of conjugate functions and conjugate duality. I like this presentation because in this presentation you get a framework in which your primal problem, the problem of creating an upper bound, and the problem of creating a lower bound are identical, are symmetric. And I think that's a very nice feature. All right, so the first point I want to make is that there is kind of a syntactical problem if you think about it. If I only give you a black box oracle to the gradient, you essentially have a map that goes from a point x in your feasible set, in your primal space, from a solution, it goes to a gradient. But the gradients don't live in the space. So it's not really clear how are you going to change your x by knowing a vector, by knowing a functional. How are you going to map a functional back to the space of solutions? Okay? So you need some kind of map that goes backwards from gradients to solutions. Okay? And you could say, just take the identity. That's what you do if you just take a step in the direction of the gradient. But in general, you need some rationale for choosing this map, and which we'll call mirror map. So let me give you one way to define this kind of maps. So what are the kind of maps that map from gradient functionals back to the primal space? So the typical kind of maps of this kind are conjugate functions. So many of you probably know this, but what is a convex conjugate? So if I have a function g, convex function here, g here in red, the convex conjugate g star is a function that takes as input really a vector, a functional, think of it as a possible gradient, and then optimizes this expression. And you can think about that as maximizing the difference between this blue line, which is the functional defined by z, and your convex function. So whenever this is maximized, this quantity, this translation, is g star of z. more interesting than G star of Z is what the gradient of G star of Z is. So let's think about that. The gradient of G star of Z is, well, if you think about it, by optimality condition, so think about the maximizer U for this expression, by optimality conditions, the maximizer U has to obey this first order condition. You know, if I differentiate here, I get the gradient of G at my maximizer must equal Z. And it turns out that this maximizer U is actually the gradient of G star. So all of that to say that the easiest way I have to think about this conjugate function, which is under mild assumption, like this actually only works for strictly convex functions, is that G star, the gradient of G star, is the inverse of the gradient of G. Okay? So I'm gonna, in some sense, these require some assumptions, but all the proofs I'm going to show based on this fact can be easily generalized to the more general case. So we're going to work with this throughout this talk. Think of the gradient of G star is simply going to be the inverse map of the gradient of G. This is going to let me talk about maps that now take gradients and bring them back into primal space. And there is a similar definition for concave functions that I actually, this comes in the next slide. And another useful thing to know is that under very mild assumptions, the dual of the dual, the conjugate dual of the conjugate dual is the function itself. And there is a similar concept for concave functions, and it's essentially exactly the same, except you have min instead of max. Okay, so now that we have covered the conjugate duality, let's go back to our problem. You know. So what should I put here? And the idea is that I'm going to think of some map psi, some function of psi, and the gradient of the conjugate of psi is going to provide this map back. And I'm going to call this the mirror map, and this the mirror function psi. Okay. So this is kind of important because the intuition for why there are lots of different ways of understanding what the role of psi is. First, kind of psi is going to allow you to define to have a simple definition of a notion of lower bound of a dual notion through conjugate duality. Algorithmically, kind of, you're going to think of psi as a problem that's easy to solve, because the whole point of introducing this psi is that the gradient of psi star is something you can compute. So the point is that I'm going to assume from now on that I can compute this map from some psi. Okay? So psi, this immediately means that the psi is an easy function to optimize over, because if I query the gradient of psi star at 0, I'm just going to get the argmax of psi. Psi is concave. So psi is an easy function to optimize with. And this also means that you can actually formally think, if you do things carefully, you can actually formally think of psi also as a preconditioner, in the sense that if psi is close to f, this is, the fact that psi is easy to optimize makes it easy to optimize f. And good. So that's some intuition about psi. And then the last thing in conjugate duality that is actually very useful is to understand, for the purposes of discretizations, we need to understand if a function f is smooth, what can we say about its conjugate? And it turns out that if f is convex and smooth, its conjugate is convex and strongly convex, with a 1 over R strongly convexity parameter. Okay, so that's the background. Now we're going to start deriving some algorithms. Questions?
How the Hessian of the function
So that's they're related also by an inverse relation, but that's a bit more complicated. And in general, they don't have to be twice differentiable, these functions. Any other questions? All right. Okay, so let's start working with actual problems. And the kind of optimization problems I want to solve first are called composite optimization. So these are particularly nice for this framework I started to sketch because the objective itself has a composite form. So the objective is minus some convex, minimize some convex function minus some concave function. And these functions are exactly the ones that I have access to in my black box. So in some sense, I have an oracle, a gradient oracle that takes me from solutions to gradients for f. And I have a gradient oracle that takes me from gradients back to solutions for psi. And what we're going to care about is whether these map and this map are smooth or non-smooth. So what's an example of like a typical composite problem? Is suppose you have a smooth optimization problem over a polytope. So smooth function over a polytope. Then you can write it as minimize fx. This is the smooth part. And this is just the indicator function of s. Okay? So that's the function that's 0. It's a convex function that's 0 on the polytope s and plus infinity everywhere else. Okay? So these are going to be in this, my f and my minus psi. And we assume that we have access to the gradient of f. What does it mean to have access to the gradient of psi star? But the gradient of psi star has this definition, because this is the indicator. The gradient of phi, the mirror map is exactly this problem, which is just linear optimization over S. Okay? So the way the mirror map works is you give me a gradient, and I'm going to find the point that minimizes that linear function over the polytope. So this is going to give rise to Frank-Wolf methods, which we'll do next. And in this case, what do we know about our maps? We know that this f is smooth, so this map here is Lipschitz continuous. This indicator function it's a very non-smooth function because it goes from 0 to infinity, and it's not hard to see that its mirror map is also non-smooth. We have a setting in which in one direction we are smooth and in the other we are non-smooth. Okay, so
Lorenzo,
yeah.
Question from Twitter. Someone is asking, how is psi related to f?
So psi, it's just something that we have to assume you are given. In practice, you will want to design psi, and we'll get to that. But psi, it's something that we assume is given. In this context of composite optimization, phi is actually part of the objective. So psi is actually concretely given.
I mean, you motivated psi star in a different way earlier, so why should the mirror map correspond to this part?
Well, this is I mean, clearly, if you have this kind of function, this is a natural way of the composite in this way. This kind of more general view of what the psi is will come more into play when you don't have a composite problem, when you just have a problem like this. And then you need to come up with a psi yourself. And we'll cover that later. So composite optimization is a very restricted setting because, you know, the two oracles that you have, the primary and dual oracles, also come from the functions that are in the objective. In general, that's not true. In general, you'll just have convex function, and you'll need to come up with this. And that's where the intuition about preconditioning comes in. Good question. Any other questions? So what are solutions? So as we construct our solutions, again, let's go back to this kind of syntactic way of the problem. We're going to get a bunch of primal points, and we're going to maintain our current solution x bar. And these primal points, I mean, the only way in which we get primal points is by querying our mirror map. So to have iteration, we're going to get some primal point, and you can actually show that the right way to construct x bar is by taking some distribution, some convex distribution of the primal points you've seen so far. This can be actually can be made formal. And for this reason, I'm going to define x bar in this way. So let me parse that. Okay, so what is alpha? So I'm going to think of kind of the timeline. So this is 0. And in some sense, I want to allow myself to give different weight, different importance to different points in this timeline, or kind of get different speeds. This is also going to be useful for discretization. And that's the whole point of defining this alpha. This alpha is really just a measure over the timeline. So this can be the cumulative distribution, and it would be alpha of t. And alpha prime of t, it's the density function. And we'll figure out later what alpha is to be. Actually, we'll need to figure it out when we discretize. But this is just a convenient way, actually, of not talking about step lengths, but keeping all step lengths 1 and working with the alpha to define the scale. Okay, so another thing I want to mention, so I'm trying to create a convex combination of these points. The reason I'm adding x0 is because I want my dynamic to be differentiable at time 0. So essentially what's going to happen is from time 0 to time 1, I'm going to stay at x0. I'm really giving a weight of 1 to the point x0. And then I'm going to give a weight of alpha dot of t to all subsequent points. In this way, this becomes a convex combination. Is that clear? Because this will come up a lot, I'm just going to use this Lebesgue notation. Okay. So I have some measure over time. So this is going to be the way I define x bar. This is actually convenient because when you actually prove this formally, you can easily turn this into a discrete measure. And most of the proofs go through. So it's very convenient for discretization. It's exactly the same picture on the dual side. I'm going to get a bunch of dual solutions, z's, by querying gradients. And I'm going to maintain my current solution as an average of the z's. OK, so finally, we are ready to define some upper bounds and some lower bounds and some notion of duality gap. OK, so what should I take my upper bound to be? So the most natural choice is the function value at my current solution. So remember, my function is f minus psi. So my notion of upper bound would be f of x bar minus psi of x bar. And you can differentiate that. And this is the derivative you get, but this is the way in which the current solution changes. So this is all great when you do discretization if f and psi are smooth. So if these guys don't change too quickly. If these guys change quickly, you'll not be able to discretize. You won't be able to integrate this, which you need to do when you discretize. So instead, say for example, that psi is non-smooth. So if psi is psi star is not smooth. So if this map is not Lipschitz, sorry, no, right. psi is non-smooth, so if this map is not continuous, not Lipschitz continuous, we need to do something else. And that something else is going to be this nice trick, which instead of using f of x bar and psi of x bar, I'm going to keep f of x bar because I'm assuming f is smooth. And instead of using psi of x bar, I'm going to use the fact that x bar is an average of points. And I'm going to use Jensen's inequality to use the average of the psi's at the points that make up x bar. So this relies key on the fact that this current solution I'm maintaining is an average of things. So while the evolution of psi x bar may be non-smooth, once I start bounding it by an average of things, this things is smooth. This is a way of taking an upper bound, which is non-smooth, and using concavity in this case, turning it into one, which is going to be smooth, although it is going to be much weaker. It's going to actually lead to slower algorithms, but things we can discretize. Okay. Any questions about upper bound? So this point is important. Okay.
With the integer function example,
But in the integer function example, all the points you see are inside, so it's not a problem. Are inside the polytope. Yeah, exactly. Okay, let's talk about lower bounds now, and about what's the, how I want to construct lower bounds. And so the following is really, I'm going to show that there is a special function you can write of gradients that defines a lower bound, and that's a consequence of this conjugate framework we have introduced. So for a convex function, how would you go about designing a lower bound? So the way you would go about designing a lower bound is whenever you query a point and you get a gradient, you have a lower bound for your function. If you're optimizing over some, say, compact set, you know that the minimum of this functional provides a global lower bound to your optimization problem. That's a dual solution. Same works if you have a bunch of points, so distribution over points you queried. You can take all these different lower bounding hyperplanes and take their average. Their average is still a lower bound. Then you can minimize that average, and that will give you a global lower bound for your function. So the point is that the notion of a dual solution is a convex combination of gradients. What is not nice about this is that if I want to evaluate what my lower bound is, I need to keep around all this stuff, all this other information, which is not a gradient. So conjugate duality helps you simplify this expression. And the intuition is this. Okay. So I did this for f, but I can actually add, because I care about psi, I can now add psi on both sides of my expression. And then I can minimize on both sides. So when I minimize, then I know that f of x star minus psi of x star, which is my optimum, is lower bounded by this expression, where now I have a minimization over u in here. And the minimization includes psi. So this is the kind of the key trick in this conjugate duality, is that now this term here looks like a conjugate dual or something. And actually, you can make this term also look like a conjugate dual, and you get this lower bound. You get that your optimum is at least psi star, so the conjugate dual of psi, of an average of gradients, minus f star of an average of gradients. And so this average of gradients is what I'm going to think of as my dual solution. So when I think about a dual solution, I'm going to take some average of gradients and plug it into this function.
How did you go from the first to the second?
From here to here? Yeah, so here, this is for all u. So this is for all u, and I just took it by adding psi u on both sides. And then here I minimized over u. And so when I minimize over u, I'm going to get this min here. And the min is going to involve my psi of u. So I get, what I really get here is the conjugate of psi at this average of gradients. And what I get on this side is the mean of fu minus psi u, which is opt.
But alpha moved inside because
the alpha, the alpha moved inside, doesn't matter. It didn't fit in that doesn't matter. I also moved it inside because I wanted to emphasize both this and this are an average. Okay, so essentially what we derive now is a way to think about a dual objective. And that's a nice feature about composite optimization, and kind of the whole reason why I went down this route, maybe for good or for bad, is that there is a clear way of defining a dual function based on where the solutions for the dual are convex combinations of gradients. So the symmetry between primal and dual is what I like in this framework. And now, same reasoning as in the primal case. This guy and this guy may be smooth, may be non-smooth. You'll get the problem, you can check. Based on whether they're smooth or not smooth, you'll choose your lower bound as either being the function value or the average of the function values at the point z. Remember, z bar is an average of the z's. You really care about psi star z bar. These may not be smooth, you cannot discretize it. If that's the case, you use this lower, smoother lower bound. Okay. Any questions about all of this? All right, let's see if we can push and actually do Frank Wolf before lunch. Okay, so let's apply all this big cloud of potentially useless notions to the smooth optimization over a polytope. So again, in general, you have a gradient oracle, and you have a linear optimization. You have this gradient of the psi star. And so the main defining characteristic here is that your f is smooth and your psi is non-smooth. Okay? So let's use that. That means that my upper bound should look like this. Should have f of x bar, because f is smooth. And then it should contain everything else in the upper bound and lower bound should be the average. So here is the average of the psi's, and here is the average of the psi stars and the f stars. In some sense, what's happening here is that in this problem, between f and psi and f star and psi star, the only thing which is smooth is f. And that is reflected in my construction of lower bound and upper bound. I'm going to choose my, the only place in which I'm not using an average is for f of x bar, because f is smooth. Okay? So once I tell you this, everything, now the algorithm will come out by itself. Let me show you why. So I define this. Now I have a notion of gap. And now there is this invariant, which is important. This is going to be kind of the invariant in all these algorithms. And the invariant is alpha t. You can think of it as just time times the current gap. So this, I claim that our algorithm will preserve this quantity. Why is that helpful? If actually I can show that the algorithm preserves this quantity, that I know that after time t, my gap must be the initial gap over alpha of t. So as alpha of t grows, I'm reducing the initial gap. Okay? So I claim that this is a natural notion of an invariant you might like to keep. And actually, this is the invariant that all these first-order methods maintain. Okay, so let's Now, the rest is an exercise in differentiation, and for this example, I'm going to do it with you to show you how it works. So remember, my invariant is alpha t plus 1 times gt. I'm going to look at the contribution from the upper bound and the lower bound separately. So in my upper bound, I'm differentiating with respect to time this quantity. And what I get, so I have two terms, one from the smooth function and one from this averaging. And they're going to differentiate in this way. So this term, I have to apply the chain rule. So I have to apply the product rule. So I'm going to get two terms. Here I differentiated alpha, and here I differentiated the function. So I get the inner product of the gradient and x bar dot. For these guys, differentiating these averages is really easy because you can use the fundamental theorem of calculus and you just get psi of xt. So notice again, an important thing, the only part of your rate of change in which you see a gradient is the smooth part. Everything else is just averaging function values. And lower bound, in the lower bound, everything was non-smooth, so it's just one big average. And this is what I get. So now I put them together, and I have this expression. So this comes from my smooth part, and this comes from my non-smooth part. And now, remember that we have defined x bar to be the average of these points that came from the mirror map. So based on this, you can actually, you know what x bar dot is. You know this quantity. And so here I just differentiated x bar to get x bar dot. And now I'm going to plug x bar in there. And I'm going to get this simpler expression. And again, there is a smooth part and a non-smooth part. So what changed is that this alpha t plus 1 canceled this alpha t plus 1, and this term got replaced with this term. OK, so now, if this is truly an invariant, I want this to be 0. And it turns out that there is only one way you can make this 0. And by using conjugate duality. And the idea is that if you look at f and f star and psi star, you really want these to be conjugate pairs. What do I mean by conjugate pairs? I mean that I mean this. I mean so that xt is the map of zt. Why do I want that? Because if that's true, that means that phi star of zt plus phi star of xt minus zt xt is 0. That's by the definition of the conjugate dual. So if I make this choice of xt, I know that
Is it phi of x?
Psi of xt, not psi star.
Yeah, thank you. So I make this choice so that I can cancel out these two terms, and I'm going to get a ztxt component. So all this non-smooth part becomes f of s. I get this ztxt. And then same reasoning on the smooth part, but now I don't have just an average of functions. I have some gradients. And what's going to happen is that for the smooth part, I'm going to need zt to be the gradient at x bar. And again, because these are conjugate pairs now, I get this expression, and everything cancels out. And I get 0. So this choice of maps makes this an invariant. Actually, the right way to think about it is that if I tell you this invariant, you can derive that this must be the dynamic. And why is this? What's the point of this dynamic? So this is the kind of picture you want to keep in mind. remember, your gradient of f, your f is smooth. So what's going to happen is that the algorithm is going to take the current solution, query the gradient at the current solution. So it's going to get this gradient. And then it's going to take the very same gradient and map it back. Okay? Notice that this z bar, which is the current dual solution, is not a part of this dynamic. It sits there, it certifies things, but it doesn't, you're really not using it. Okay? The reason for this is that this map here is non-smooth. So if you were trying to apply the gradient of psi star at z bar, you would end up with something that you cannot discretize. And that's why this picture looks like this. Okay. Okay, so this is, what does it mean in terms of smooth optimization over a polytope? So we have this picture, and these are the definition of the dynamic. So what it means is that I have some solution x bar. I query the gradient. This is the gradient which we call z of t. Then I apply the mirror map at zt. So applying the mirror map means I optimize this linear function over the polytope. And it's going to give me xt. Xt is this point. And then what happens is, because x bar is an average, I'm going to add a bit of x into x bar to get my new x bar. And this is exactly Frank-Wolf. And this also allows you to think a bit about problems like, can we improve Frank-Wolf? And here you can the main issue that you can see here is that this map psi star is non-smooth, and the reason why it's non-smooth is that the boundary of this polytope is non-smooth. There are these vertices. If you had something round, then this map would be smooth, and you could do better than this.
So the choice of alpha didn't play a role in...
Not yet. That will come in a discretization. That's for the discretization. Okay. Okay, so we'll do discretization, and then we'll take a break, and I'll let you digest your lunch and this. Okay. So the nice thing about thinking about upper bounds and lower bounds in terms of either the function value or the average of the function values is that when you discretize, the only terms you make an error on are the terms that look like this. So whenever you're using averages, you really don't pay, there is no discretization cost, because in some sense, this is a Lebesgue integral when you average over function values as an exact discrete counterpart. You're just averaging function values in discrete time. But this guy here, this really depends on the gradient at xt. This part you won't be able to discretize exactly. And so that's why when you do discretization, we'll think about what happens when I go from this continuous integral to a discrete version. So again, I only need to worry about the blue part, which is the smooth part. That's by design. I design my function so that I only need to do this. So here it's the integral from going from time t to t+1 in continuous time. And what the most basic thing I can do is forward Euler. And what does that mean? It means that instead of actually trying to compute this red curve, which is the actual integral, I'm going to take the gradient at time t and just estimate this integral as this blue box. And this, I'm going to get this discretization error. And you can actually show in this case that the discretization error is always positive. So the picture actually looks like this. Okay, so what does that mean in practice? So here it's how it's going to work. We're going to go from a continuous measure to a discrete measure. I'm going to call it A. A is going to be the density. Capital A is going to be the cumulative function. Averaging, this averaging remains averaging in the discrete sense. And you can actually think of it this way. And then these two definitions don't contain derivatives, so we can just stick to them. And now I'm skipping like 2 lines of computation that are pretty easy, actually. And so to just give you an expression for the discretization error, remember that this is our invariant. We really want this to be 0. And it turns out that if we apply this discretization scheme as I defined, you get this discretization error. And this is nice for many reasons. First, it really involves, you have the f, the gradient of f, and then your mirror map. So it's a natural thing to get. And then, so in some sense, once you get to this point, you can do a number of things. It really depends on what kind of smoothness you have. What do you know about the problem? So here is actually the place where lots of fast algorithm for specific, say, linear programs will diverge. If you have more structure, you can do something different here. What people do in general in optimization is they use this definition of smoothness and strong convexity that I told you before. And if you use that as your notion of smoothness, then your next step would be to apply Cauchy-Schwarz. And then you can apply smoothness on this side. And you get this kind of expression. Then here, this is the difference between 2 current points, between 2 averages. So you can simplify that. Just going quickly through the computations. OK, and you get to this point. Now here you get xt and x bar t. These are 2 mirror maps. So all these points, both these terms are distances between points within your polytope. So these are really, you can replace it by the diameter squared. So this is the kind of discretization error you get in one iteration. And then you just need to choose finally what these a's or what these alphas are going to be. And it turns out that if you want to balance things right, the right choice of a is essentially linear with I. And you get this kind of bound. And notice that this bound here, so because I is I, capital A really scales like t squared. So if you only add the continuous dynamic, you would have this kind of convergence. This term here comes from the discretization. And this is actually the bigger term. This is what dominates. So this shows that Frank Wolf, if you want to take the gap down to epsilon, you need t to be like L, the diameter squared, over epsilon. And then you can bound this term. This term, you can show it must be smaller than this. And so I like, this may seem like a lot of work to recover a simple result, but once you're at this point, you can do many other things. For example, there is a different notion of smoothness people use, which is called Holder smoothness, where instead of having norm and norm, you have a norm and you have norm to some power. Same exact analysis, you essentially use the same scheme. You're going to use Holder's inequality instead of Cauchy-Schwarz, and you get this bound, which is also the right bound for this case. If you have a different notion of smoothness, which comes from your specific problem, you can use it here. Okay. So I'm going to stop now, and then after lunch, I'm going to talk a bit about dual averaging, which is the dual counterpart of this, and about acceleration and a few open questions.
Comments for Lorenzo?
Can you have a line search in your analysis? Because in order for things to cancel, you need to set them fixed, right?
Mm-hmm. So I haven't thought about line search. I have examples where you can definitely have adaptive step length, but I haven't thought about line search. You can have step lengths which depend on the size of the gradient you just squared. Right. So that we'll talk about it after lunch. When you get into accelerated methods, forward Euler is not enough to get the right convergence. And then you have two choices. There is a little trick which gives you Nesterov's accelerated gradient descent. And then there is a way to go it that's more like approximate backward Euler, which also gives you the same kind of convergence. So that's a good, we'll talk about the kind of discretization techniques that are helpful is an interesting area of research.
So the 1/t term showed up because of discretization.
Yes.
Is this intuition correct that acceleration is all because you want to deal with the discretization part? Otherwise, if you're living in a continuous domain, there's no need for enzyme.
In a continuous domain, things are complicated because you can really have arbitrary fast.
Because you already get 1/t squared without any.
So on an intuitive level, there is some truth to that, but I cannot quite make it exact. Or like almost on an algebraic level, if you go to the proof, your intuition is correct. But I don't know really how to make it formal.
If there's no further question, let's thank Lorenzo again.